Okay, section 8.2. We're going to be integrating powers of trig functions. Let me summarize what that means, for us at least. There'll be three different types of problems we'll be doing. First up, we'll have powers of cosine and or powers of sine. Okay, I'm going to have to figure out what to do there. That itself is a whole section. The other trig functions we'll be looking at are secant and tangent. So powers of secant together with powers of tangent. And or. So it could be that only one of them is there and not the other guy. M and N are positive integers. Not any kind of fractions or radicals, nothing like that. We're talking about positive integers, not even negatives, just positive integers. Okay. The third type of problem isn't powers at all. Okay. It's when you have sine and cosine, but inside the angle, they may be multiplied by different numbers. Sine and cosine, or sine and sine, or cosine and cosine. You can't call that sine squared because the angles are different. One has an mx and one has an nx, and the m and n are different. And we'll say that one for last. That might even be for Monday. If we make it through the first one. We'll probably end up making it through the first one today, and then maybe these other two for Monday probably. We'll see. Whenever you get through the day, we'll be exam ready. You know what I mean? I won't teach you anything on Monday and expect you to have it down for the exam on Wednesday. I won't do that. Okay, so we're going to get through part of this, and the part that we get through will be something I can examine you on. Okay? My goal is at least to make it through one, perhaps one and two. We'll see. All right, let's take a look at one. Powers of cosine together with powers of sine. And we'll see how to break it down, like how to decide what to do based on the numbers that are the exponents. Based on m and n, that tells us where we need to go. All right? So let's first take m and n to be one of them odd, one of them even. Doesn't matter which one. When there's a mixture of an odd and an even, this is what we should do. We're going to find out later there's probably a better way to put it all together, but here it is. So one of them is odd and one of them is even. Here's an example. Cosine is to the fifth, but sine is squared. Okay? Basically, whenever there's the presence of one odd, here's the algebraic technique we need before we even get started. It's all about identities. We're doing this. You have to pull identities seemingly out of nowhere. And these identities are to help you do your integration. Okay? Here's how it works. Focus on the one that's odd. The one with the odd power. And I like to think about it as peeling off, but you're factoring out one of the powers. So if I have cosine to the fifth, I'm going to factor out one of those and leave it as cosine to the fourth times the cosine. Okay. Now we'll see why we're doing this. Notice that we're not doing anything to the one that has the even power. The reason why we do this is because the one that we peeled off, the one that we factored out, basically we're going to end up doing this just with the U substitution. And this taking one of them out ends up being part of the U substitution. For the rest of it, for the even power that's left over, this is cosine to the fourth in this example, just use your Pythagorean identity, sine squared plus cosine squared is 1, and transform that. So it's like I have a cosine squared and another cosine squared. If you want, you can call it cosine squared squared, or you can put two of them out there. Here I have them, the whole thing squared. And I have the red being the one cosine that I took off in the beginning. Okay? Yeah, either way, you can leave it like this or have it as cosine squared times cosine squared. And either way, it's still 1 minus sine squared that needs to be multiplied out by itself. I'm going to leave it like that, though. 1 minus sine squared, the whole quantity squared. I see people left. Okay? Now, what about that other sine squared? We never touched that one. So here's the deal. We're going to do a substitution now, letting u be the one trig function that you didn't touch. If you let u be sine of x, then what ends up happening is basically a polynomial here, and what's the derivative of sine? It's cosine. So you're going to use u substitution to finish the problem out. Let u be the other trig function, the one you never factored out from. So let u be sine of x. Okay? And then we'll have some polynomial in u to integrate. Let's take a look at it. So I had 1 minus sine squared squared, and then I also had this sine squared here. This is my original sine squared, and then all of this is taking the place of my cosine fifth. This guy right here. I'm going to let u be equal to the sine of x. And what does that do for me? That makes this guy a u squared. It makes this guy 1 minus u squared, whole thing squared. And because du is cosine x, the reason why I peeled off that 1 was because it's going to be part of du. So cosine x dx will be exactly what du is. And I can integrate that all day long. It doesn't look like it, but you can. Multiply it out. So that's the method. If there's an odd present, you attack the odd by peeling off 1. That 1 you peeled off is going to be part of du. The others that are left over, transform them into the other trig function, and let u be that other trig function. You're leaving yourself with a polynomial in u, which you can integrate. We love integrating polynomials. You give me a polynomial integrate, I'm happy. Okay. This is 1 minus 2u squared plus u to the fourth. And I got another u squared here. I guess my polynomial in the end is going to look something like u squared minus 2u fourth plus u to the sixth. Okay, I have it all typed. I just want you to sort of see the scratch out work of it too. I'm going to erase this and then have the nice typed up version of it. But that's the idea. Okay, attack the odd, peel off 1, leave yourself with an even. Trade the even powers in using sine squared plus cosine squared is 1. Trade it in for the other one. Let u be the other one, and you'll be sure to have a polynomial in u to integrate. Okay. Integrate polynomials all day long. Question?
Can you go back a slide, please?
Back a slide?
Yeah, it's what you just had written on the bottom.
Oh, I don't know if I can.
Oh, that's all right.
Sorry. This is basically what I had on the bottom.
Okay.
I just had it not as neat as that. Okay, multiply that guy out, and you got a nice polynomial to integrate. U cubed over 3, minus 2u5 over 5, plus u7 over 7. Done. Trade back in what u is, and you're done. That's the antiderivative. Okay. So, attack the odd by factoring 1 out. You'll be left with an even. You gotta get rid of that even, trade it in for the other one. Using sine squared plus cosine squared is 1. And then take your other one that you didn't touch, plus these that you traded in, do a u sub on that, and you're guaranteed to have a polynomial in u. And the reason why you peeled this 1 off, so it can be part of du. And this method is used when one of the powers is odd. I know it says 1 odd, 1 even, but we're going to see that if they're both odd, we do the same thing anyway. Okay, so when 1 odd is present, this is the attack.
And this always has cosine.
We're talking about only cosine and sine involved. Maybe you won't even have the other one, but at least right now we're dealing with cosine and sine. We're on number 1. When we get to number 2, we have different rules.
But like I'm saying, it always uses this identity for this particular.
When there's an odd present, we're going to use this identity. We'll see that when there's no odd present, we got to use another identity. Okay? All right, so the next example is going to have both of them odd. But it'll be the same attack. Yes? If you don't put the C at the end, you get points off on the exam. What is it? Half point. It's not technically correct. But it's open. It's not open-ended. It's going to be multiple choice. So you know. I don't even give these really. I give limits of integration. I don't really even give indefinites. If in your work you forget the plus C, I'm okay with it. In the answer, though, it needs to be there if it isn't indefinite. All right, now both of them odd. But this is just the same as the last one, okay? The present of the even doesn't change things. It's the present of the odd which gives you this attack. All right? So have them both cubed, say. This time, though, I'm going to choose, I got my choice. Both of them are odd. I get to pick which one I want to peel off and do the whole substitution with. So last time I chose to take the cosine and peel off one of that. This time I'm going to choose to take the sine and peel off one of that, just so you can see how that works. Question?
Is there any benefit in choosing one or the other?
Not when they're both odd. Not when they're both odd. You got to choose an odd. Pick one. Randomly. Doesn't matter. No benefit. If they're the same power, if one's a different odd power, it doesn't matter. Pick one. And do what with it? Peel off one of them, factor out one of them, and leave the other even power still there. Sine cubed is going to be sine squared times sine. But I can't leave that sine squared like that. I go to the identity. Sine squared plus cosine squared is 1. And I trade it in for the other trig function. I go and call it 1 minus cosine squared. This is all me attacking the odd power, the one I chose. It's the same technique, though. Okay, this is the technique that you use when there's an odd present. Whether the other one's even or whether the other one's odd, so what? This is the same technique. So what are we doing now? Well, now the other 3 cosine powers and now this blue part, 1 minus cosine squared, that's going to be all u's. I'm going to let u be cosine. Why? Because the one sine that I peeled off is going to be part of du. You got to be careful, though. Because now, if u is cosine, du isn't sine. Du is -1 times sine. We got to carry that negative through. Okay? So let me do this patchwork again, and then I'll have the nice typed up. This guy's going to become u cubed. This guy's going to become 1 minus u squared. This guy, I like for it just to become du, but it is not. It's negative du. Please stop texting. That's not bad. So just distribute the negative u cubed across, and you have your polynomial. We have negative u cubed plus u to the 5th. And I like to integrate polynomials. I'd much rather integrate polynomials. So it's the same. It's nothing different from what we did last time. Okay, yeah, I chose the sine, but I chose the odd. And I want you to see what happens if you choose the sine as your odd. You just have to remember about this negative. I should have made this negative a different color. I have to really focus on it. I want you to see that negative is there. You see it? Okay. Questions? Here's the thing that I just erased. Multiply it out. I think that's what I had. Is that what I had? Not what I had at all. I wish I could go back. Let's do it again. Why did I not have that? U cubed, 1 minus u squared. I want to call this du. I had this negative out here. I integrate that. I distribute this across. negative u cubed plus, oh yeah, that's what I had. It just was the other way around, I just switched them. U to the fifth minus u, the same thing. With the plus sign, I can switch them like that. All right, we're good. Sorry about that. So yeah. Anyway, I have this polynomial. I get polynomials all day long. U to 6 over 6 minus u to 4 over 4. Final answer, 1/6 of cosine to the 6 minus 1/4 of cosine to the 4. Done. Presence of odd, attack that odd, kill off one, and work it out. It'll be in polynomial integration in U. When there's not an odd, just trouble. This is actually good. When there's an odd, that's a good thing. This isn't that bad, comparatively speaking, what we're about to do. Okay? When there's not an odd, things get a little difficult. Let's see it. Questions about this before we move on? Got time to write all that down? Yeah.
So that negative that's in the front, that just comes from du.
That negative comes from du. This negative here that's in the front comes from du. Good question. And then I distribute it across. Oh, I guess I switched these around. That's weird. Okay, I guess it works too. Anyway, you end up with u to the fifth minus u cubed, regardless of how you do it. Maybe you want to call it minus u cubed plus u to the fifth, whatever. You end up with the same thing though. And that's your final, that's your antiderivative. And you need to go through that process. There's no shorts changing. There's no shortcut to skip over. You need to go through that process. And that's actually good. Just when there's an odd present, that's a good thing. Yes?
How are you able to switch u squared minus 1 around?
If I take negative of a minus b, oops, it's b minus a, right? I got negative 1 times a minus b. That's b minus a. Okay. It's minus a plus b. You okay with that? And I just like to switch it and have it this way. You don't have to do that at all. Please don't. You know, if you don't like it, don't do it. Sorry about that. Son. Turn it down. All right, we're good? All right, so what about when there's not an odd present? They're both even. Cosine to the fourth and sine is squared. I don't know why this animation is off like this. Anyway, both of them are even. Cosine fourth, sine squared.
Oh, yeah.
Totally abandon the last technique. No peeling off, no u sub, no sine squared plus cosine squared equals 1. Abandon all of that. Okay? And use a different identity. I don't know if it's called the half or the double angle, but there's a I'm gonna call it half angle here. You gotta use this identity. That sine squared could be replaced by half of the quantity of 1 minus cosine of double the angle, or cosine squared is replaced by the same thing but with a plus sign. Okay? And that's how you attack your even powers. The problem with this example, though, is that I have cosine to the fourth. So it's like I have two cosine squares. It's like I have a cosine squared, and a sine squared, and I use the above identities on each one of them. Think it's messy. Okay. I'm going to trade in cosine squared for the identity above. If I have two of them, one and then another, I have to multiply that out. And then I'm going to have sine squared traded in for the other identity above. Yes. Let's work it out. Instead of me click, click, click animating through the animation, let's work it out. All right, you ready? Cosine squared is half of 1 plus the cosine on twice x. Cosine squared. Half of 1 plus the cosine on twice x. Sine squared is 1/2 of 1 minus the cosine on twice x. And I'm integrating that from 0 to pi.
They equal the same thing.
They are the same identity. One has a plus, one has a minus. The sine has a minus.
That's what it is.
And the cosine has a plus. Wow. A half, that's an eighth. Me, I like to pull constants out. So I'm going to pull that eighth out. And now I have to multiply this thing out. Okay, I got this guy, 1 plus cosine 2x, 1 plus cosine 2x, and 1 minus. I have to multiply that out. This guy times that guy. All right, 2 at a time. I'm not going to choose these first two. I'm going to be smart about it. Okay. I'm going to choose these second two. Why is that smart? Difference of squares. I got the middle term to cancel out. When I FOIL this out, I'll end up with 1. My middle term is minus cosine 2x. But then I have another middle term plus cosine 2x. And then I have minus cosine squared on 2x. So I purposely chose those two guys first because I didn't want that middle term. You didn't have to do it that way. All right, so here's what I'm looking at now. I have 1 plus the cosine of 2x, the other guy, this guy here. And now this is 1 minus cosine squared on 2x. Now I'm going to FOIL this out. Oh, there goes my plus finally. Okay, so I'm just being careful and choosing the difference of squares so I can get my, and now, here we go. 1 times 1 is 1. We get minus cosine squared on twice x plus the cosine on twice x. What's this next one here? Cosine cubed on twice x. Wow. All right. Let me tell you what you like. You like integrating 1. You might not know it, but you like integrating cosine on 2x. These other two you don't like. What do you think we're going to do with this guy? Cosine squared on 2x. Do it again. It's an even power. There's no odd present with that same term. You do it again. What do you mean do it again? Trade it in for this half angle identity. Where if you have a 2 here, you better have a 4 here. So we have this 1, and now we're going to trade this in for half of 1 plus the cosine on 4x. Oh man, what am I going to do with this one? Cubed. There's an odd. Okay, the other guy isn't there, so what? When there's an odd, peel off one, trade it in, do a U-sub. All right, there's a lot going on here. We need a new slide. This is too much. We need a new slide. All right, for a second it's going to be bad because I'm going to keep this, but there's animation underneath. Let me just keep it. Sorry. And I'm going to take it, copy it, make a new slide, and try to continue this on. If it lets me drag it up. Oh, it flipped it over. That's just not good. What? Wow, that was weird. Okay. Didn't want that. Uh-oh. Starting it. Oh, man. Here we go. All right, let me remind you where we're at now in our animation. Sorry, don't worry about what's there in the nice typed up notes. Let's take it from where we were and continue on with these handwritten notes. Okay, so here's where we're at. We have an eighth on the outside. We have a 1, and there was a minus sign here, and we traded this cosine squared on twice x in for half of 1 plus the cosine of 4x. And then there was a cosine on twice x term. What was the sign on it? Okay. And then there was a cosine cubed on twice x. Very good. Okay. So now what do you like? You like integrating 1. Let's distribute this across. This is minus a half and minus half of the cosine of 4. You might not know it, but you like integrating that. You'll like integrating this. We said that earlier. 1 minus a half, well, let's just call it a half. You like integrating a half. You don't know it, but you'll like integrating this guy. And you'll like integrating this guy. This is an issue, but we know how to handle it. We peel off 1. Cosine on twice x. We make the other one cosine squared. Don't forget it's a minus, though. What do we do with these cosine squared? We trade in for sine squared. 1 minus the sine squared. And we could do a U sub on that. You peel 1 off. I should write in a different color. The one I peeled off, I was writing in red. You peel 1 off, but it's not a cosine x, it's a cosine of x. And you take the other one, let me write that in blue. I think I was writing that in blue. You take the other one, which is even at that point because you took out the odd. You take the other one, and you trade that in using the Pythagorean identity, not the half angle identity. Sine squared plus cosine squared is 1. So cosine squared is 1 minus sine squared. So I trade that in for that. I still got this minus here to deal with. I'm just trying to show you how the setup is. And I'm going to do this whole thing with a U sub. So this whole thing here is going to be done with a U sub. These guys don't need that U sub. But don't forget, you have an eighth, and it still is the integral from 0 to pi. Okay, let's handle this part that's supposed to be the easier part. These parts that you like, maybe you don't know, but you do. What is the antiderivative of a half? 1/2 x. See why you like it? What is the antiderivative? Uh-oh, be careful. Cosine of 4x. Keep the minus half out there. What is the antiderivative of cosine of 4x? What function has cosine 4x as its derivative? Sine 4x. But you need a fourth. So an eighth of sine of 4x is what that ends up being. What function has cosine 2x as its derivative? 1/2 the sine of twice x. When we found the antiderivative of these guys, we can lose the integration. We could say from 0 to pi. And there's the 1/8 out there. This other part we have to deal with still with the u sub. But why is this so nice? We should have seen this happening. I'm going to tell you how we could have seen this happen. Sine, what are my limits of integration? They are 0 and pi. And what am I plugging these guys into? Sine. Sine of 4 pi, sine of 2 pi, sine of 0, sine of 0. It's all going to zero out. I should have known that somehow. I shouldn't have to go through all this work. It's hard to see, but if you integrate a full period, or maybe 2 periods of a function that is periodic, sine and cosine, they're going to cancel out the areas. What is the period of cosine 4x? The 4 will squish the period in. You go from having a period of 2 pi, and it squishes it in by a factor of 4. Your new period is pi over 2. This thing completes a whole cycle by pi over 2. So if you're integrating from 0 to pi, you got 2 full cycles. Area is going to be 0. How about cosine of twice x? It takes you from period being 2 pi to period being pi. Integrating the full period of cosine. It zeroes out. We should have seen that. That's okay if we don't see it. Now we see it though. These guys zero out. What's the result of all this? After these guys essentially zero out, what's left over is this guy. And it's pi halves. Okay? There's still this 1/8 out here. And there's going to be a 1/8 over here on this guy when we do our little u sub. But that's going to zero out too. Not as obvious to see though. Let's work that one out. Where are we at in this process? There was a minus sign, yes, and there was this 1/8 out here. I just put them both here together. Hopefully that's okay. And I want to work this u sub over here. I just got to be careful. What do I let u equal? What's the purpose? I peel off the thing so it can be part of du. So I let u be the other thing. Sine of twice x. I peeled off the cosine so cosine can be part of du. If cosine is part of du, then u must be sine. U is the sine, but I got to be careful, sine of twice x. So this guy becomes 1 minus u squared. That's a polynomial. I can integrate that all day long. I don't know where it went, but there it is. And this guy will du. Derivative. Derivative of sine? Cosine. I'm sorry, I know. Derivatives, integrals all in the same prime. It's absolutely ridiculous. It's hard to keep straight. But. Chain rule? There's a 2. All right, so you're going to need a half. This guy, cosine 2x, will be replaced by half of du. I don't know where the half is at. There's the half. Okay, and now you integrate that. And you integrate that, and you get half of u minus u cubed over 3. So we get half of sine twice x minus 1/3 of sine twice x cubed. But we don't care because we're going from 0 to pi. We just don't care. Oh, where this thing went? There was a half here. There we go. We just don't care because we put a pi, we put a 0 in, and they just zero out. Final answer, pi over 16. All that for that. Question?
I had a question on when we were asking cosine to the 3 and 2x.
Cosine to the 3 of 2x.
If you also have done a half angle identity, like separating it and make it like cosine x squared and cosine x, and using one.
So we did this. We separated it. But remember, the purpose of this separation is so we can do u sub. We don't do a half angle on this. When there was an odd present, we didn't talk about half angles. We said we use sine squared plus cosine squared is 1. Not half angles. This trigonometric identity, this Pythagorean identity is the one we use.
But if you did a half angle, would you be wrong too?
Yeah, because you still got a u sub. You still got this guy here that you didn't do anything with. We never talked about using that identity when we had an odd present. Don't introduce it now. You're not making up a new formula for it. Use the old one. It's not going to work the other way. That's why we never did it that way. Don't do half angle if there's an odd present. If there's an odd present, use Pythagorean identity. It becomes a simple u sub at that point. When there's an odd present. We didn't have an odd present in these other guys, and that's why we went for this half angle like crazy all over the place. Don't get them mixed up. Odd present, no half angle. No odd present, half angle. Odd present, Pythagorean, no odd present, half angle. I'm going to have a nice, pretty typed up thing. Here it is. And then I work through each individual. Then I work through each individual integral here. And it's all nice and typed up really nice. It looks all nice and everything. Anyway. There's the answer, pi over 16. Okay. Question? Yes?
It won't always cancel out, will it?
No, needs to be a full period or multiple periods to cancel out. That was the key behind the manner. There are essentially 4 integrals here. This is a full period, this is a full period, and this ends up being a full period. We don't know what these functions look like though. Cosine squared, we don't know what that looks like. But definitely cosine twice x, we know what that looks like. And we can honestly say that that's a full period. The period on cosine twice x is 0 to pi. We should not have had to integrate that. We should know it's 0. On this one, we don't know, but it ends up being a full period. It is periodic. It's just not something that we know. So we should go through all the work of how it works out. Even, half angle. Odd, no half angle. Keep it separate. Ultimately, that's what it ends up to. But they all zero out. Something happens here, though, in this one. But we already incorporated into ours when we got our 1 minus a half. We got our half, and it worked out for us. I did them each one separately here. But when we did them, when I worked it all out, I took the half from this cosine squared and combined it with the 1. That's why it looks a little different. But the same thing is going on there. So, see how things are zeroing out. Okay, and then finally, so odd present, you go through the whole u sub, no odd present, half angle. What about if one of them, this is a gift here, if one of them has the power 1, this is a gift. y. U sub. No crazy identities. Just straight U substitution. The other part is already there to be the du to the first power. No peeling off, no half angle, Pythagorean, no identities, just U sub. Let U be the one that's to the power. Let U be cosine x. If they're both 1, I don't care, choose one. Let U be cosine x. So the other part is there to be du. Well, not exactly du. Negative du. But so what? And we're looking at u to the 10th times du, well, times negative du, which is u to the 11th over 11. With the negative out there. And you're done. Trade it back in for what u was. What was u? Right? All right, we have limits of integration. Let's plug them in. Pi and 0. Now be careful. We're to the 11th power. I don't even like writing it like that. In fact, I hate writing it like that. I don't know why I did that. If I had my way, in fact, I'll probably redo it. This should be cosine x to the 11th from 0 to pi with a negative 1 over 11 on the outside. What's cosine pi to the 11th? Cosine pi by itself is negative 1. Negative 1 to the 11th is negative 1. All right, cosine 0 is 1. 1 to the 11th is 1. But they don't cancel out. They double up to be a negative 2, but this negative out here from du, the answer, 2/11. It's a gift. If one of them has the power 1, you should thank me if you see something like that. I'm being nice. Probably won't be on it. All right, great. That's what the picture looks like. Let's send you to it. Yeah. All right, I gotta start a tangent. Secant. Sorry. Well, I'm going to say I won't put it on the test. I got to start it though. I can't stop class now. But from 8.2, you got to worry about point number 1, powers of sines and cosines. For next exam, you have to worry about what's coming now. But I can't just end class though. Powers of tan and secant. Don't totally tune me out. But there's no pressure of having to know this down by a week from today. You gotta stop signing your friends in. Somebody skipped out. Alright, we'll let it go, I guess. Okay, tan and secant powers. Different game. Forget about everything you just said. Different. Don't try to think it's the same. Okay? Power of tangent. We're going to focus on that. When the power of tangent is high, we launch into all of this. When it's even, Power of tangent I, we're going to launch into all of this. What is it? Well, first off, what's the identity that relates these two? We know sine squared plus cosine squared is 1. What's the Pythagorean identity for secant squared and tan squared? Tan squared plus sec squared is 1? No. 1 plus tan squared, secant squared. Let's write that down. 1 plus the tan squared is the secant squared. Okay. What we're going to do is reminiscent of what we did. It's not exactly the same, that's all. Because the identity is different. But same idea. We're going to factor out one of them. Okay. Here I'm looking at tan cubed and secant cubed. Factor out 1 to tan and make it tan squared and tan. All right, so factor out 1 power of secant and 1 power of tan. Okay, so I factor out 1 power of tan, I'm left with tan squared. I factor out 1 power of secant, I'm left with secant squared. You got to ask yourself, why? Well, why did we do this kind of thing last time? So we could do a U substitution. We're headed towards a U substitution. And the stuff that we factored out in red is going to be part of du, like we did before. What function has secant tangent as its derivative, though? That's going to be du. The red is going to be du. Du of what? What trig function has a derivative of secant tangent? Okay. If your function is tangent, what's your derivative? Secant squared x. Okay, great. If your function is secant, what's your derivative? Secant x tan x. All right, can't forget these things. We need these things. Cheat sheet material. Okay? What's in the red is the derivative of secant. I'm going to let u be secant. So then what's not happy? If u is secant, then these are happy. This guy is going to end up as u squared. This is not happy, though. We need to trade this in using that identity. Okay? What's tan squared? Tan squared is secant squared minus 1. I can't leave that tan squared like that. That's why it's in blue. I got to get rid of it. I got to trade it in. But the secant squared, I'm happy with that. That can stay as secant squared. So that's in black. The red is part of du. The black is going to stay part of the integral. But the blue has to go. The blue trades in to become secant squared minus 1. And I'm going to let u be secant. And I got a nice polynomial in u. So it's sort of the same. But not exactly, though. Let u be secant. And we're looking at u squared minus 1 times u squared du. Let u equal secant, so that du is secant tangent. Distribute this guy across, and you got a nice polynomial in u. U fourth minus u squared. Integrate that all day long. U fifth over 5. U cubed over 3. You're done. Go back in and trade it in for what u was. What was u? Secant. A fifth of secant x to the fifth. A third of secant x to the third plus C, and you're done. Not bad. But tangent's power has to be odd for you to go through all that. Okay? When it's even, but when tan is odd, you go through this. Let me just tell you, the book has none of this. You trying to read this from the book? No, none of this. I even have examples. And they expect you to cover it. Here.
Oh, you.
Yeah, you're right. Yeah, just, download it later. Be all right. You good? Alright. Let me just set this next one up and we're out of here. Power of secant even. Okay. Power of tangent odd, go into all of that. Power of secant even, go into all of this. Same kind of thing. I'm integrating secant to the fourth tan squared. Notice, power of tan is not odd, so I don't launch into all of that. Power of secant is even, I'm going to launch into all of this. You tell me, you should probably figure it out by now. The power being even, you're going to factor out a secant squared because the derivative of tangent is secant squared. The thing you take out is part of du. It's in red in every one of these slides so far. Part of du. You're going to let u be tan, and you're on your way. These tan, they'll be happy staying as tan. The secant squared, the other guy that is not part of du, this will be part of du. This other part can't stay like that. It's blue. Blue needs to be traded in using the identity. What identity? 1 plus the tan squared is the secant squared. So trade in for that for 1 plus tan squared because we're about to do a let u be tan. Tan squared stays as tan squared. Sec squared gets traded in for the blue, 1 plus tan squared. The sec squared that you factored out stays as sec squared because that's going to be part of du. We'll do a u sub. Let u be tan. Because this guy is going to become u squared. This guy is going to become 1 plus u squared. I'm happy with that. This guy is du. I can integrate that all day long. Distribute. And you're talking about u squared plus u to the fourth du. U cubed over 3. U fifth over 5. Go trade it back in. And you're done. Okay? What calls this? Power of secant even. We'll call the other thing power of tangent odd. Right? If you don't have that, then you're out of luck pretty much. Okay, there's no rule for anything other than that. So officially we're done with 1 and 2. I'm not going to hold you responsible for 2 until later. I'm going to hold you responsible for 1 though. Okay, I'll come up with an assignment for you for the fourth whole hand in. But it won't be due on the day of the exam. It'll be due the next Monday or something like that.
Can you leave that on there?
Which one?
The last. Oh, and parents, you guys just play, and